Okay guys, so 6.2 today, and we're going to look at using our integration skills to find the area between two curves. So there's three diagrams on the screen now. What I'd like you to do is just think about how you could find the area of each curve, each shaded area in the diagram, and write down a integral involving the functions that you can see for each of those areas. As soon as you've done that, start the video again, we'll move on. Okay, so into your notes. Remember, when we're using fundamental theorem of calculus, when we're looking at areas beneath curves, we're looking at continuous functions. If you think about it for a second, asymptotes would really mess things up. You end up with this infinite area as the curve heads closer and closer to the asymptote. So we're looking at continuous functions. And what we're looking at here is f of x greater than or equal to g of x. Well, if that's the case, like in this diagram here, the shaded area I is going to be what maybe we would guess it's going to be. It's going to be the integral of f of x take away g of x dx. If we think about that, well, the area under f of x is all of this, and the area under g of x is this, and so the shaded area is the bit that remains when you take the green away from the red. So subtraction works. We've got to be a little bit careful though when we don't have this, when the curves cross, because then we've got to pay careful attention to which one is on top. So, just color coding here. Where I've got red, so I call this like I1 and I3, and I call the green ones I2 and I4. The red ones have F being greater than G, whereas the green ones have G being greater than F. So if I wanted to work out the total area here, so the total that's shaded, so shaded area, well, that's going to be I1 plus I2 plus I3 plus I4. But we've just got to be a little bit careful of that, because for I1, it's, you get this right, F take away G. But for I2, it's G take away F. For I3, it's F take away G. And for I4, it is G take away F. So we have to reverse it each time. And so when we're doing these calculations, we just need to be a little bit careful. But if we are using our calculator, then actually there's a way to do this easily, so we don't have to split up the functions each time. We can use the absolute value function inside, and so if I were doing this same question, I could just integrate between a and b, but look at the modulus, the magnitude, the absolute value of f minus g over that range. The calculator uses a numerical method to solve integrals, because it's giving you inexact values. So because it does that, it can integrate a modulus function very easily. If we're using non-calculator method, it's too hard. Okay, so a bit of integration practice. You've done this, and we've got two questions on this page and the next one. I'd like you to pause the video and have a go. Okay, so we're trying the first one here. Always good to do a sketch. Let's see, what does this look like. So, x and y. The two functions I've got are x squared plus 1 and 4 minus x squared. So, I'm going to kind of have relevant points here of 1, 2, 3, 4. So, 1, 2, 3, 4. 4 minus x squared, well that's going to cross the x-axis at 2 and minus 2, so we can do it like this. 2 and 2. So that's going to look something like this. This is y equals 4 minus x squared. Whereas the other one, x squared plus 1, it's going to look something like this. And then we are looking at the limits for 1 and minus 1. And so our shaded area, what we're looking at here is this space shaded in red. So I don't know what kind of shape you would call that. But if we're working out our integral, then we're going between minus 1 and 1. And when we're doing the subtraction, this is just designed to show us that sometimes it's useful actually to do the subtraction inside before we integrate. So it just makes our life a little bit easier. So 4 take away 1 is 3, minus x squared minus 2x squared dx. So integrating, that's going to give me 3x minus 2/3 x cubed from 1 to minus 1. And then substituting in, I think we get 3 minus 2/3. Substituting in the 1, take away minus 3 plus 2/3. And then that's what, 7 over 3 plus 7 over 3. So that's 14 over 3 units squared. So, yeah, for some questions works out easier to do this subtraction inside the brackets. Let's have a look at the next one. So area of the region enclosed by the graphs f of x equals x cubed and g of x equals x. So area enclosed means we're going to have to do a sketch to figure out what our endpoints are going to be here. So drawing on y equals x, and then I've got y equals x cubed, a cubic. So it's going to look like this. And if we think about where it crosses, well, it crosses at x equals plus or minus 1 and at 0. So this point here is going to be 1, 1. This point here is going to be minus 1, minus 1. And it says that area enclosed. So it's this red area here. So I guess first thing that we could do is we could say, oh, it's definitely symmetrical. So I'm going to say that the area is double the area between 0 and 1 of g minus f, so x minus x cubed dx. So that's twice the integral of x squared over 2 minus x to the power 4 over 4 between 0 and 1. So that's twice. Substituting in 0 is obviously going to give me 0. Substituting in 1 gives me a half minus a quarter. So 2 times a quarter, which is just a half units squared. So hopefully all okay with that. Let's just have a quick look at what I was talking about before in terms of the absolute value function. So this same question here, if I were going to solve this on CAS, what I'm going to do is use solve. You know, obviously don't need to do it for this case, but if it was more complicated, to find where the curves cross. And then here we can see the absolute value function inside the definite integral is going to give us the correct answer if I integrate over the whole range. And you can see here it tells us that it's 0.5. Actually, two different methods here, and you can work through either of them when you're answering the questions. Okay, one last question for today, quite a short one. I'd like you to have a go at it yourself. You'll recognise the picture from the first slide that I showed you. We want the total area between the curves. Just a little tip for these types of questions sometimes is when you're answering them, you can label your work. So I'm going to label mine I1 and I2. I1 and I2. You can use the same or your own kind of labeling, but have a go at the question, and I'll go through it in a second. Okay, so first thing as we look at this is we're definitely going to have to do the integral in two parts because I'm going to have to reverse the way in which I subtract. And so one of the first things I'm going to have to do is work out, well, what is this point here? What is like A? So we know at A that cos A equals sine of 2A. Sine of 2A can use use my double angle formula. So in order for this to work out, I'm going to have sine A equals a half, or cos A could be equal to 0 as well, but if cos A equals 0, that would mean I was at pi over 2, which is this point here. That's where they meet. We need a point before that, so we're looking at sine A equals a half, which implies that A equals pi over 6. So that's the point where the curves cross. So if I'm looking at the first shaded region, the red one, I1, I'm going from 0 to pi over 6. And for this one, I have cos x take away sine 2x, because it's the upper take away the lower, the top take away the bottom. So cos x minus sine 2x dx. Integrating those, well, cos integrates to sine, and then this one's going to be something like cos 2x, but if I differentiate that, I multiply it by 2, so it's going to have to be plus a half. Thinking just about the anti-differentiation, always just being the opposite of differentiation. Then substituting in here, substituting in with pi over 6 first, I get sine of pi over 6, which is a half, cos of pi over 3, which is also a half, so it's half times a half, so 1/2 plus a quarter, and then just be careful if I substitute in the 0, the first term is 0, but the second term here, cos of 0 is 1, so this is going to be take away a half, and so my answer overall for I1 is 1/4. That's obviously half of it, because then I need to do I2. So here I'm going between pi over 6 and pi over 2, because I'm just looking at the green part. And then because the curves switch over, I do top take away bottom. So sine 2x take away cos x dx. The integral, some of the signs change, but it's minus a half cos of 2x minus sine x between pi over 6 and pi over 2. And then if we substitute in, first of all, substituting in pi over 2 is going to give me cos of pi, which is 0, sine of pi over 2, which is 0. And then as I substitute in pi over 6, it's going to be minus a quarter plus a half. So, sorry, substitute in pi over 6, cos of pi over 3 is a half, so minus a quarter plus a half. I think this is right. Plus a quarter minus a half, sorry, it's late in the evening. So overall this is a quarter, that's right, and so the total area is I1 plus I2, nice and clear and you're working out, I1 plus I2, so that's a quarter plus a quarter, which is a half units squared. Good stuff. Okay, final thing before we finish, I just want you to notice this. This is in a past exam question from year 2001, and you'll notice that one of the curves here, it dips beneath the x-axis, so you've kind of got this, in terms of the signed area, you've got a negative area going on here. But what I want you to understand is that the kind of general rule of the top curve take away the bottom curve, this works even when one of the curves is below, or even if both are below. And it will give you the overall area. So for example, if you're doing the top curve, take away the bottom curve here, because it's negative, the subtraction cancels out, and actually you end up adding this curve on. So an example for the shaded curve, the bit in red here, is just really simply the integral between pi over 4 and pi of the top 2 sine squared x take away the bottom curve, sine of 2x dx. And you know, there's nothing more complicated to it than that. Okay, well, I wish you the best of luck with the questions, and let me know, as always, if there's something you find difficult. Speak to you soon.